All right, welcome. This is the introduction to Matrix of Time Part 2. Obviously, you were intrigued enough by Part 1 that you've chosen to watch Part 2. I hope you enjoy it. So, what do we know about matter? It seems that when we look at matter, we find out that of the 100% of matter that needs to be there to justify the universe as it is, only 5% is null matter. That is the matter that is detectable by us. 27% is dark matter, and 68% is dark energy. So what does that mean? Well, dark matter was postulated by astrophysicists to account for the large amount of mass that's required to justify the gravity that explains the velocities of rotation and gravitational lensing of large objects in the universe. This amount of visible matter could not account for this, so the hypothesis is that there has to be invisible or dark matter that we're unable to detect to account for this much gravity. A CERN web site that I found said that the theory of dark matter could be considered as extra dimensions, especially dimensions that are smaller than an atom. So here we have basically 20% of the matter is invisible and undetectable to us. Now we have 68% that is also invisible and undetectable to us and is manifesting as dark energy. Now what is dark energy? The dark energy is different from dark matter, and it's also postulated by astrophysicists to account for the fact that the universe is expanding. But it's not just expanding, it's expanding at an accelerating rate. To account for this expansion of the universe, there has to be a source of energy that can sustain this expansion, and astrophysicists call this dark energy. So everything we know about space and time is based on less than 5% of the matter in the universe. 5%. Of this 5% that we can detect, 99% of it is empty space. Hold on, you say. That's a bit crazy. If I look out into the cosmos, I can see basically that it looks like it's 99, in fact maybe even more than 99% empty space. But here I am on a chair, I have a table with my laptop, and how is it that I can be sitting on this chair and my laptop can be supported by this table if matter is 99% empty? Well, there's a couple of explanations. One is that electromagnetic fields hold matter together. But there's another topic, because you say, hold on, if matter is 99% empty, how is it that I can see through it? Well, let's look at this. Let's take an example of a bicycle wheel. So we have the bicycle wheel here spinning around its hub, and you can see that if you had a light beam, the light beam easily goes through this bicycle wheel. It only has 6 small spokes, and even if you try to poke your finger through, if the rotation was relatively small, that wouldn't be a problem. But if the rotation got fast enough, you wouldn't be able to poke your finger through. It would look transparent, but you still couldn't poke your finger through there, because the rate at which you're moving compared to the spokes would be so slow that one of these spokes would always be in a position where it would prevent your finger from going through. But now let's look at matter, because matter clearly it is opaque. And what makes it opaque if everything is so empty? Well, if we do the same setup, now we take millions or billions of rotating bicycle wheels and we shine a light beam through. You could see that the first part of it, it would look transparent, and then it would get more and more opaque, because at some point there would always be a bicycle spoke in the way of the light beam, no matter where it was. And the light couldn't make it through. And this is basically what's happening to matter, that within the first few microns of the interface of matter, light is being absorbed. And yes, I mean, certain like glass is transparent. Those are other processes of physics that are going on. But this could explain why matter that's basically empty would look solid and feel solid to the touch. Okay, so we're going to dig deeper into matter. And here we have an atom. And physics says that it can be represented as a point-like object. So in other words, we visualize an electron as a tiny, say, ball spinning around a sphere which we call the nucleus. And this is the way most of us visualize the atom, and it's the way we were taught in high school and in some of the basic courses, that it just is easier for us to wrap our mind around a central sphere called the nucleus and all of these electrons and shells spinning around here. But is it really that simple? Well, quantum mechanics tells us it isn't that simple. And in fact, the theory says that an atom can behave as atomic particles, I should say, can behave either as an object, a point-like properties, or it can have wave properties. Now, what does it mean if we look at an atomic particle and it has wave-like properties? So what this means is if we look at the outer shell, quantum mechanics will tell us that there's a 90% probability that we will find the electron with somewhere within the shell. There's no way that we can predict exactly where it's going to be, but there's a probability that it's going to be somewhere in this shell, and we call that an electron cloud. Now, if you pick a particular electron shell, then it gets a little bit more specific. Here we have a dumbbell, and this would say, so quantum mechanics will predict that the electron now is in a little bit more defined location, but it's still spread out over a distributed form of space. And so here, as we dig deeper, we find out that not only do we have, such a small amount of matter that's defining space and time, but as we dig deeper, that these properties of these atomic particles, they have sort of like split personalities. They can behave sometimes as a point and sometimes as a wave. So how would we visualize this? So let's look how matter can be looked in two different forms to understand better this split personality of matter. So here we have pitcher and a couple of glasses and a glass sphere on a table. And we'll call this the particle form. And this is the common way that we interface to our universe and the way we interpret our world. But there's another way to look at it. If we look at this part right here, we would call this the waveform. This is a holographic image of the exact objects in the left-hand side. So we can see that these two forms, the waveform and the particle form, represent the exact same information. One we're familiar with and one we're not familiar with. Now, what is interesting is in the particle form, if we landed up cutting this in, say, 4, we would land up having one piece where you would have the glass in the sphere, another one that would have part of the pitcher in the other glass. The top left corner would have maybe no object information except some pieces of this light. And that part we understand. But if we took this image right here and we cut it into 4 and we took one piece and we shone laser light back through it, we would get back all 4 pieces back in the image. Now, the image might not have as fine a resolution or as bright, but we could take all 4 of these pieces, each one, do the same thing, and all 4 of them would have the exact same information in. We can do that even finer. We can keep cutting this into smaller and smaller pieces, and all of this information that's on the left-hand side would still be found here, but eventually the resolution would get coarser and coarser. The edges would become more grainier. So in the right-hand side right here, you can think of the electron in its distributed form, and that the information that is the electron is distributed everywhere. There's no position here where the information of the electron is not. The same way that there's no place here where the information of these objects in the left-hand side is not. So it's a very different way of looking at matter. And with the proper technique, again, you can extract this information. There's, mathematics that take you back and forth between the two. But what I'd like to do is introduce a couple of terms to look at this. On the left-hand side, we called that the particle form when we related it to the atom. And on the right-hand side, the waveform. But typically, in physics, they talk about a local form or the local aspect, local property of matter. And in the right-hand side, it's the distributed form or the non-local. And so when you see these terms, we're going to shorten them to local and non-local, and we'll use particle and waveform to really help you understand the two different formats that matter can exist in. So let's have another look at two views of matter with a different technique. This one is called Fourier Transforms. Those of you that are in the technical field will be familiar with it, but you really don't have to understand the process of Fourier Transforms. All you need to do is look at these images and understand. So here we have, again, we have Mickey Mouse, and we'll call this the particle-like or local form. Then we do this mathematical transform called the Fourier transform on it, and Mickey Mouse is now in the wave-like or non-local form. And so this, again, exactly the same information. It's not the same as holograms, but the information that represents Mickey Mouse over here is now distributed in a form that we don't understand, or I shouldn't say we don't understand, but we're not familiar with if we didn't understand the math behind it. And you could say, well, how is the information stored in here? Can we figure out where at the center of this distributed information, what's in here versus the edges? Well, actually we can. So what we can do is we can put a filter on this information, and we can then block out everything except the center, and then we can do a transform back again, and what happens is we basically get the outline of Mickey Mouse, but all of the details are gone. You can't decipher his fingers. If there was much more details on here, creases in the clothes and fine facial features, all of those would be gone. You would only get this really rough outline. And say, well, what happens if we do the inverse? What if we block the center and only take the outside? So now we're going to see what is the information that's stored on the outside edge that relates to this image called Mickey Mouse. And here we see that here's where all the fine details are sorted out. So what this does, it takes an object that we're pretty familiar with and stores it in a form that's distributed. It takes this information and puts it in a form that we're not familiar with. But again, so if you keep this in mind as we go forward, that what quantum mechanics is telling us is that we only are familiar with one form of matter, and that is its particle-like object form or local form. The distributed wave-like or non-local form is not familiar to us, but these two examples maybe help you visualize better what matter would look like in this other form. So let's summarize what we have learned. Only 5% of matter is detectable. Of that 5%, 99% is empty space. The 1% of matter that we can detect manifests as a split personality. One time it is a point, another as the matter is distributed as a wave. And this is the basis on which we base our understanding of the universe. All right, so after a little bit of a interesting dig into matter and finding out how little matter we can actually detect in the universe, let's go back to something that we feel a little more familiar with, and that is space. I mean, after all, you're sitting here watching a video on your laptop. You're either sitting on the couch or, in a chair behind a desk or a table. You can see that you've got walls that are attached to a building. You look outside and you see nature outside. So at least this should be more fundamental. Well, I can imagine not such a big surprise, but that space is invisible and undetectable. And as we show here, everything is black. There is no structure. If we land up putting a rectangle in space, the first thing that we can start to do is we can define space. We can say, there's something to the left of it, and there's something to the right of it. There's something that, if you add more matter, you could say it's above or below. And so now we start to give space some structure. Can you imagine now if we land up creating a volume, not only it makes it a little bit easier to do up and down, but now we can do inside and outside as a new definition of space. So before we had nothing, now all of a sudden we put a little bit of matter into space, and we're able to do some definitions. But these definitions we're giving are dependent on a frame of reference. So let's assume that you're standing in front of the door some distance, and you look at this this building, and you say, "Huh, I know where up is, and I know where right is." Now, is it that straightforward? Maybe not. What if you were above the building? You would then look at it, and you'd say, well, up is this way, and right is that way, different than the other person. And so what would happen is you can, at least in this circumstances, you can say, okay, we know how to transform my point of view to your point of view, your reference frame to my reference frame. We can now say relative to the building, we can define a structure for space with X, Y, and Z, and we can say, okay, I'm looking at this from Z, you're looking at this from X, we transform it. Now this is how up transforms into this coordinate frame, and how right transforms into that coordinate frame. So with this example, you notice how motion changes how you see objects and also how you would define them. Let's investigate this a little bit more. So in this next example, let's start off with a train and a caboose on the train, and let's, for assumptions, assume that one side of it has a one-way mirror. So we can see in, but the people inside can't see out. And so the train is moving down the track, and the person inside is bouncing a ball up and down, catching it, throwing it down, catching it, throwing it down. And this example here represents that. Now, if we bring in an observer, the person in blue, they would see the same thing that the other person who's throwing the ball up and down does. The ball goes straight down, straight back into their hand, even while the train is moving forward. Now, what if we take a different point of view? What if we now put the observer outside on the track and we have the train moving through? What are they going to see? They're actually going to see something completely different. They're going to see the person throwing the ball down, and as the ball is going down towards the floor, it is then moving to the right-hand side. It bounces up from the floor, it continues moving to the right-hand side and back into their hand. So this would have more of a parabola shape instead of this linear motion up and down. So when the observer and the person doing the action are both in the same frame of reference, whether it's stationary or moving, doesn't matter, they can agree that they see exactly the same thing. But once you have the observer outside and there's motion between the action and the observer, they see things completely different. So the question that Einstein posed when he thought of this whole process is, whose view is correct? And technically, both views are correct. They're just based on your frame of reference and whether you're moving along with the event or whether you're moving in a different direction relative to the event. So if everything in the material universe is moving, then where is the absolute reference? It seems like everything has a frame of reference, and depending on where you stand and where you observe the rest of the universe, you see something different than somebody else who is in a different frame of reference. And this was the basis for the theory of relativity, and you can see how motion can change the way you see the universe. All right, takeaway message from this video. So, less than 5% of our universe is detectable matter, and that matter is 99% empty. Of this 5%, the 1% of matter in space and in time can manifest in two forms. One as local, or as objects, point-like, and the other as non-local or distributed, wave-like. Our reference frame defines how we see the universe. Motion changes how we see what is happening in the universe. How we interpret the universe in space and time is relative to our location and the motion of the universe around us. This will be explored more in the relativity video. So in the next video of this series, we'll look into motion, this link between distance, space, and duration, time, a bit deeper. Since motion defies not only our ability to determine the structure in space and in time, but also how we see events in the universe unfolding around us, we need a better understanding of motion. Hope you'll join me in the next video. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you will see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.